Hello and welcome to my tutorial on longitudinal and transverse waves. So all electromagnetic waves are transverse, and there are other examples of transverse waves like ripples on water and waves on ropes. So two main ways of drawing transverse waves. It's showing them as graphs of displacement against distance along the path of the wave, with your wavelength, your trough, your distance on along the x-axis, and your crest here. And there is another way you can show it displacement against time at for a point where the wave passes, just like that. So this is along the path of the wave, and this is the distance against time. So in longitudinal waves, the vibrations are along the direction of travel. So longitudinal waves tend to be very common in sound, and sound waves consist of alternate compressions and rarefactions of the medium it's travelling through. So rarefactions are the parts in between are compressed parts of the wave, but all the vibrations are going in the same direction. So between each compressed part, this is one wavelength. So this naff way of doing it, having the darker areas where the springs are vibrating more than the other parts of the spring. Is one way of doing it, but they're really hard to draw graphically, as you can plot them as displacement against time, but they look confusing because they look like a transverse wave, so they're very hard to tell the difference between the two. So now we'll move on to polarized waves, where they only oscillate in one direction. Oh no, putting on the one direction puns. But if you shake a rope, on a serious note, if you shake a rope to make a wave, you can move your hand up and down or side to side, or in a mixture of directions, and it still makes a transverse wave. So here's my rope and here's the fence. The fence is sort of like my Polaroid filter. It can only vibrate up and down. It can't do it left or right because the fence is there. So if you try to pass waves with the rope for the vertical fence, the wave will only go through if the vibrations are vertical, and the fence filters out the vibrations in any other direction. So this is what's known as polarizing the wave, or getting the wave to oscillate in one direction. Oh no. So if you had two polarizing verticals at right angles to each other, then no light will get through. It's just not going to happen. It's like getting a gauze that you have in chemistry and trying to put a flame through it. It's not going to work, as the gauze sort of stops it. But that's sort of like what having a polarizing filter, like it just makes a sort of mesh that doesn't allow any of the light to go through. So this will be shaded like that, and none of the light will be able to get through. So polarization only happens for transverse waves, and the fact that you can polarize right is the proof that it is a transverse wave. So when you reflect the light now, it's partially polarized. If you rotate the polarizing filter in a beam of light, it shows the fraction of the light that is vibrating in each direction. And if you direct the beam of polarized light at the reflective surface, and then you view the reflected wave through a polarizing filter, the intensity of light leaving the filter changes with the orientation of the filter. What that basically means is if I keep rotating it, then I'll have a different intensity light, because of the amounts of lights in at the angle that you're pointing the Polaroid filter at. It doesn't matter which angle you're looking at it the light at, it's what angle the Polaroid filter is at. With orientation, rather. The intensity changes because the light is partially polarized when it is reflected. So the unpolarized light comes in, and when the light reaches the glass block, it's reflected and then polarized out again as partially polarized light. So as the polarizing filter is rotated, the intensity of the light leaving the polarizing filter changes. And the effect is used to remove unwanted reflections in photography and Polaroid sunglasses to remove glare. And if you can afford them, they will save your eyes a lot. So now is a real life example. Television and radio signals are polarized. So you look at a TV aerial, it sort of looks like this, and it has little bars coming out of it like that, and there's the wave going down to the cable all the way down the chimney to your TV set. And you line up the rods on the receiving area with the rods on the transmitting area. If they aren't aligned, the signal strength is lower, but because of the little bars, it's allowing the waves at horizontal plane to be received easier. But that's one application to it. But if materials could also rotate your plane of polarization, as I've mentioned before. So if you have a light source and a beam of light, arranging the two polarizing filters so that no light leaves the second one, and there's another light source and the beam of light, if you place a material between the two filters, so some of the light gets through the second filter, but if you rotate the second filter until no light leaves it with the material there, then the angle you rotate the filter is the angle the material rotates the plane of polarization. So that's it for this tutorial. We went through longitudinal waves and transverse waves and how they're different and how you can't draw longitudinal waves. We also looked at polarized waves and how they could be an example of transverse waves, and we also looked about how materials could rotate the plane of polarization. So I hope you found this tutorial useful. Thank you for watching.